All right, here we are today, starting off the next area that we study. We're going to look at and complex numbers. All right, so first lesson here is just some reminders of some definitions and things from what you would have done last year in Unit 1. So let's get on with that. So complex numbers, complex number systems, it says there. Expressions which have no real solution. Okay, so we often work in real numbers only. So like methods, for example, always real numbers. So central to a complex number system is the definition I squared equals -1. Also, then that means that I is the square root of -1. So we can use square roots of negative numbers. We can find them in the complex number. Now, this bit here, I squared equals -1 and I equals square root of -1. That's kind of what, so here is Euler's identity. So this is how he wrote this: e to the I pi plus 1 equals 0. Right, so that's really where it all comes from, this identity. And as it says there, most beautiful equation in mathematics, considered by a lot to be, because it's one equation, is in these 5 constants. So e, I, pi, 1 and 0. So 5 pretty important constants all put together. All right, anyway, that's a little bit of an aside. So for us, in what does it mean to us? It means essentially this bit here. That I is the square root of -1, or I squared is -1. So therefore, if we have some thing like this, for example, square root of -16, then what we can say is we can say, all right, well, that's -1 times 16, and you would have done this year, last year, not this year, 16 times I squared, and so 4i when we've square rooted those things. All right, so another thing here, so say square root of -5, for example, will be the same thing. We're going, so square root of 5 times I squared, square root of 5 just to stay as that third, and I squared, of course, can be I. So we'll do things like that with it. All right, here it says your calculator can do this, so that, poorly worded by me, your calculator can do complex numbers. So on your, let's go to our main screen. So here we go. So down the bottom here, this one, real, complex. All right, so it just goes backwards and forwards, real and complex. And it does make a difference with you working in the real world, number world, or the complex number world, is whether it's in there or not. So if you're going back to methods and you leave it in complex, it could give you some different stuff. And one of those different stuff things would be a graph. So if it's in complex here, you try and graph something, it will be graphing it on the Argon diagram, not on a Cartesian plane. All right, so anyway, I'm waffling, so let me go back to what we were doing. All right, definition of a complex number. So a complex number's got 2 bits, a real bit and an imaginary bit. So the real bit here is the x, the real part. And so if you see this notation, R, E, and then Z, so the real part of Z, so that's x. And here I M Z, the imaginary part. So the imaginary part's a bit next to the I, so that's y. And we wouldn't actually need to put the I down. So here's some examples here. So Z equals 4 minus 5i. What's the real part of Z? Well, the real part of Z is is simply 4. What's the imaginary part of z? So the imaginary part of z is the bit with the I, and that's simply -5. All right, don't need the I. We already know it's the imaginary part because that's what we've been told here. All right, so then if we want to do this sum here, the real part of z minus the imaginary part of z, so the real part's 4, minus the imaginary part, and the imaginary part's -5. And as we know, we can put those together, 4 plus 5, and so that's 9. All right, so you can do this, you can do that on your calculator, you can find the real and imaginary part. So the real and imaginary parts, if you go to your main screen, action, complex, where are we? There we are, complex, real part, imaginary part. All right, so real part of 2 minus 3, and then if you want an I, go here, maths 2, there's your I. Alright, put that in complex just in case, then go EXE, so the real part is 2. Alright, so there's that. I wasn't going to do that, but anyway, done now. Alright, so next, what do we got? So represent -5, square root 5 as an imaginary number. Alright, so that's simply kind of what I did before. So square root of -5, square root of 5 times I squared, root 5i. That is the imaginary number. Alright, so then say something like this, simplifying, so for b, 2 root -9 plus 4i. So what we're going to do is we're going to change the -9, and so that's 2 root 9 times I squared plus 4i, 2 times 3i plus 4i, that'd be 6i plus 4i would be 10 i's, or 10i I should say, as the complex number. Alright, so we would have done all of this last year in units 1 and 2. Quality of complex numbers, so this is makes a bit of sense, of course. So if you've got two complex numbers that you're told are the same, a plus bi equals c plus di, then they're only going to be the same if and only if the real parts a and c are the same, the imaginary parts b and d are the same. All right, so if and only if those two bit a and c have got to be equal, b and d have got to be equal. So if and only if means that has to happen, and that's the only time they could be equal is when that happens. All right, so if we've got an example here, and we're told that these two are the same. So from what we saw up there, they can only be the same if and only if the real parts, which is 2a minus 3 equals 5, and the imaginary part, which is 2b and 6i, 2bi and 6i, that those things are exactly the same. So 2a, 8, a has to be 4, and over here b would have to be 3. So the only time that those two things would be equal is when a is 4 and b is 3. Any other values, they cannot be equal. All right. Here's the next one. Operations. Again, you've done these kind of things. So if you've got additions and you want to add two together, then what we do is we add the parts. All right, so if we're wanting to add Z1 and Z2, then we look at the real parts, A and C, and we add them. The imaginary parts are B and D, and we add them together. And same if we were subtracting. With Z1 minus Z2, then we would subtract. Alright, so multiplying by scalar. So scalar is just a number as opposed to a vector. Okay, so that's why we're using the word scalar. And so remember, we do vectors here in Special as well. So it's just a number, kind of numbers we're all used to. So if I just want to, here's Z, and here's K, some number, and I want to know what K times Z is, then I'm got, multiply simply both components by the Z. So if if you went back a step, it's kind of, there's a step in the middle there, isn't there, that I haven't put in. So K times A plus BI, and then we multiply K in like we normally would when we do a binomial expansion. All right, got some sums to do with that. Hopefully I've left enough space here. All right, so for A, Z1 plus Z2. So if we're adding those two together, 2 minus 3i plus 1 plus 4i. So if I go there, I'm looking at the real bits, adding them together. 2 plus 1 is 3. Then I'm looking at the imaginary bits, adding them together. Negative 3 plus 4 is plus 1. So 3 plus I is how we would write it. All right, the next one, Z1 minus, so 2 minus 3i, and we're subtracting 1 plus 4i, 1 plus 4i in this case. Again, real parts, subtract 2 minus 1 is 1. Imaginary parts, minus 3, take another 4, minus 7. All right, so then this next one, first of all, we're multiplying by a scalar, a number. So 3Z1 is, I'm gonna create myself some more space because I'm not gonna, so 3Z1 is 3 times 2 minus 3i, and we're taking away 2 lots of 1 plus 4i. So 6 minus 9i minus 2 minus 4i, and we look at our components. That's 4 minus 9 minus another 4 is minus 13, I hope. Well, what have I done? Oh, I've mucked up. I have mucked up a multiplication back here. Let's go back, because minus 2 times 4 is minus 8i. All right. So 6 minus 2 is 4. Minus 9i minus another 8 is minus 17i. All right. Just saved myself there. Okay, Argon diagrams. I briefly mentioned Argon diagrams before. So the Argon diagrams is the complex number equivalent to the Cartesian plane. So remember, they're actually different. All right, so that's why when you go to your calculator, you have to remember, there's my Argon diagram down there that I'll get to, but I'm going to so your Cartesian, that's X and that's Y, and they're both real numbers, yeah? But for our Argon diagram, this is the real part of Z, and this is the imaginary part of Z. All right, so your calculator setting makes a difference here, because it will graph different things depending on the setting. If it's set in real, it thinks it's doing this. If it's imaginary, it thinks it's doing this. All right, so horizontal axis is the real axis, the vertical is the imaginary. And there's a couple of examples. So A is 3, so 3, that's only a real part. And so if there's only a real part, it's got to go on the real axis. So if you think that's that A, for A there, you think that is 3 plus 0i. And B is kind of the other, where there's no imaginary bit. So, well, sorry, there's no real bit. And when I say no real bit, well, that's not technically correct, is it? The real part's 0 plus 2i. Now, of course, we're not going to write 0 plus 2i, are we? Well, we don't need to write the 0. If there's nothing there, we know that it's 0. All right, so then for C, down here, 2 minus 3i, so the real part's 2, the imaginary part's -3, so there's our real number C, 2 minus 3i, represented on the Argon diagram. All right, so this form here that we've been using, A plus BI, is known as the Cartesian form. And that's simply because of the similarity between the Argon diagram and a Cartesian plane. All right, there is another form, polar form, that we'll get to a little bit later. All right, multiplication. So again, we've multiplied this last year, so this is just a reminder. So we perform this in the same way as we would do an expansion of brackets, and the normal rules of algebra apply. Okay, that's handy, isn't it? So for this first one, for A, solution for A, 3i 5 minus 2i, whoop, not 25, 2i, 2i. So we go on 3i times 5, 3 5s are 15, that's 15i. And then we go that times that. 3 times -2 is -6. I times I is I squared. Now, as we know, I squared is equal to -1. So effectively, that's 15i minus 6 times -1. And that there is a positive number 6 plus 15i. And the convention when we write these things is we put the real part first. All right, so then the next one is 2 brackets, 2 plus 3i times 1 minus 5i, and so then we use the FOIL or whatever other method you use. So for me, I go 2 times 1, which is 2. Then I'll go 2 times -5i, so 2 times -5 is -10, and the I is there, of course. Then I'll move to this one, 3 times 1 is 3, and the I is there, of course, and then I'll go those two. So positive 3 times -5 is -15, and I times I is I squared. So what have we got? We've got 2 minus 7i, and then this last bit here, remember I squared is -1, negative times, and then times the negatives of the positive. So we've got 17 minus 7i. All right, so hopefully that's jogged a few memories from last year. And so that's exercise 4A questions that are on your work plan.